Okay, welcome everyone to the afternoon session. Our first speaker will be Herman Verlinde.
Almost. Can everyone hear me? Yeah, okay. So, I want to thank the organizers for putting together this very stimulating meeting. It's always exciting to see how many new developments there have been in the field. I'm going to be talking about something I've been working on for a number of years, and indeed it's still a development that's happening currently. So I'll do a tiny little bit of review, but indeed since the topic I'll be talking about is double-scaled SYK, which has been around for a bit. And when I talk about dual perspectives, of course there are various motivations of thinking about duality. My motivation is coming from the fact that if you look at double-scaled SYK, there are basically certain, you can call them almost experimental facts about double-scaled SYK that hint very strongly at an interpretation in terms of de Sitter gravity. And obviously, having a quantum dual potentially to de Sitter gravity is an interesting thing to study further. And indeed, there have been other people that have been thinking about this. Again, Leonard Susskind will be giving a talk after this. And we have indeed slightly different perspectives on this connection. I'm going to be talking about what I call double-scaled SYK in the strict double-scaling limit, which means that we're taking the number of Majorana fermions strictly to infinity. So my version of double-scaled SYK, indeed, will have only one parameter. Let's see if I have a little arrow here, which is labeled in terms of the interaction order, which is p. So there's p squared over n, which is kept finite, and that's called the double scaling limit if n goes to infinity. And that theory only depends on one parameter. And then the idea is that this theory, again, since it's soluble, should be able to compare it with potentially dual systems that themselves are also soluble, and that should also depend on just one parameter. In recent work, it's been clear that there are indeed sort of connections with this one-dimensional quantum mechanical system in the double scaling limit, and a two-dimensional system, which is Liouville gravity. It's called a complex version of Liouville gravity for reasons that will become clear in a second. But then indeed you can lift it indeed to a three-dimensional interpretation in terms of pure de Sitter gravity. And in some cases, the more practical formulation of that three-dimensional theory is actually SL2C Chern-Simons. And we're going to see that these things are kind of really very quantitatively connected, because all of these theories indeed effectively only depend on one parameter, which is this parameter Q. And one can do computations on each of these sites. And in particular, for today's talk, in order to keep the story somewhat sort of self-contained, I'm going to be talking mostly about the partition function. So I'm going to give you indeed dual perspectives on the SYK model, where I'm going to make a match between quantities that one can compute in these dual descriptions that are going to be exactly matching with the double-scaled SYK partition function. Slightly surprisingly, even going from 1 to 2 to 3 dimensions seems like a bit of a jump, but there's even sort of a close connection, as it turns out. And again, this is sort of more like an experimental fact between the quantities that one can compute in double-scaled SYK and a natural object that one can compute in four-dimensional gauge theory, which is known as the Schur index. And it turns out that indeed, precisely if you take pure Seiberg-Witten theory, which is SU2 n equals 2 Yang-Mills theory, that the Schur index has a close relationship in the fact that there's even an equality between the Schur index in 4 dimensions and the SYK partition sum. And this can generalize potentially to more other objects. Let me still introduce sort of the parameters. In this case, what's going to happen is that this parameter Q on the gravity side in 3 dimensions will basically govern the Newton constant. So the Q to 1 limit would indeed be the classical limit, and that's part of the reason why it's called Q. And it's also known that in 2-dimensional gravity, there's a natural parameter Q. But notice here that this Q parameter here is real. It's a number between 0 and 1. And here, typically, if you have a Chern-Simons theory, there's a natural Q parameter, which is e to the 2 pi I over k. What means is that that k has to become imaginary to have a match between the two systems. And the imaginary property of that k is precisely that indicates that this theory has actually positive cosmological constant rather than negative cosmological constant. And also in the Liouville theory, it means that this b squared becomes also imaginary, and that actually makes this thing complex. So let me just get started. And basically what I'm going to do, I'm going to essentially make a circle through this diagram. There's a lot of things to talk about, so it will be a little bit of a bird's eye view, but I'll try to do at least some computations that indicate to you what the evidence is that we can really sort of equate quantities on these various corners. So double-scaled SYK, people have seen the SYK Hamiltonian before, again in terms of n-Majorana fermions, and then indeed in this double scaling limit where p squared over n is finite, it turns out that the theory literally sort of simplifies quite a bit, and there are various two, or at least complementary, although equivalent ways of characterizing that. One is that in that particular limit, it's called then the collective field theory, the bilocal collective field theory that captures the interaction of the two-point function, the average two-point function of the fermions, can be captured indeed in terms of an effective theory that's often called the G-sigma theory. But this G-sigma theory in this particular limit becomes equivalent essentially to a Lagrangian that looks quite familiar, which indeed is a Liouville theory, or at least the Lagrangian looks like that of a Liouville theory, but it lives on this bilocal space. Tau 1 and tau 2 are the locations of the fermions, but the kinetic term here indeed looks off-diagonal in tau 1 and tau 2. So in this kinematic space, this is a Lorentzian theory. But it turns out that this effective theory that one can derive essentially by this collective field theory method indeed has a real coefficient in front of the action. So it behaves as if it wants to be a Euclidean theory in terms of the pre-coefficient of the action, but in terms of the kinetic term, it's a Lorentzian theory. And that actually indicates that this is indeed a theory, a Liouville theory with a complex central charge. So it has an imaginary coupling constant. Now, if you take Liouville theory with an imaginary coupling constant and you compute its central charge, you get an interesting sort of number, namely that this thing can either actually take one of two values. It's a complex value, 13 plus an imaginary or 13 minus an imaginary number. And that's indeed the theory that lives in 2 dimensions that already will have, of course, close connections with SYK, because here it actually appears within SYK. And indeed, in beautiful work in 2018, late 2018, Berkus and collaborators, they basically solved this particular double-scaled theory in terms of a combinatorial sort of approach, where you basically start computing the moments of the powers of the Hamiltonian. And the idea from the point of view of SYK is essentially doing perturbation theory. Since the J couplings are Gaussian, they lead to Wick contractions. And those Wick contractions basically in the large n limit also guide the index contractions between the various fermions. And therefore what's called a chord here is not literally a Wick contraction, it's sort of a Wick contraction of this J, but it involves many of these Wick contractions between the fermions. And then precisely in the double scaling limit, what will happen is that when these Wick contractions intersect, then something non-trivial can happen, because then in some cases the fermions that are running in this chord can have the same index as the fermion that runs in that chord. And if you keep track of how many minus signs you're picking up because of the Fermi statistics, you find this beautiful chord rule that when 2 chords intersect, you just get a factor of Q. Now, in the double scaling limit, again, this J just sets an energy scale. This really is the only number that survives, n over p squared. N itself has been scaled out of the problem. We're going to be interested in this talk only in quantities that remain finite in this strict limit. It turns out that, again, the explicit formulas are actually somewhat important for my story. So this is one slide where at least I show some formulas. combinatorically, it turns out that one can sort of look at these chord rules and look at how the Hamiltonian acts on a formal state we introduce that basically keeps track of, if I slice to this thermal disk, it's labeling how many chords I'm intersecting. And then if the Hamiltonian acts, it can either add a chord or it can subtract a chord. And if you keep track of the combinatorics of the interactions, then this turns into that particular recursion relation, where this is a Q-deformed integer. And if you look at this, you immediately recognize something that looks like a harmonic oscillator, except that it's a Q-deformed harmonic oscillator. And indeed, essentially, if you want to solve the SYK model, the only thing that you need to do is to remember your quantum mechanics class about the harmonic oscillator, and you just put a Q in front of it. But it turns out that the Hamiltonian, indeed, since it has the raising and the lowering operator, is not the Hamiltonian of the harmonic oscillator. It's like the X operator of the harmonic oscillator. But it's Q-deformed, and it turns out that because of that Q-deformation, that the spectrum of this Hamiltonian is no longer the real line, because X would have the real line, but indeed, at finite Q, it actually is naturally parameterized by means of an angle. And the spectral density of the SYK model, you can sort of think about it as indeed the spectral density of the coordinate of a harmonic oscillator, which in the ground state would be a Gaussian spectral density. Because of the Q deformation, it becomes a periodic Gaussian, which is the theta function. So that kind of gives you already immediately information about the exact properties of this double-scale theory. And you can write down indeed a partition function, which in the sort of the standard notation is written like so. This thing is called a Pochhammer symbol. Essentially, this thing is equal to that theta function up to a factor of sine theta or so. And then you can have indeed the energy sort of weighted by an inverse temperature, and that gives you the partition function of double-scaled SYK. Now, these formulas have been around for 5 or 6 years. Now, our field, again, is very sort of diverse, and we've been working on many things and making very interesting progress. But one of the things that took, in my mind, a little bit longer than I would have expected is that there's another set of developments within string theory where people look at objects involving things like that I had on the first slide, the Schur index, knot complements, and there are other kinds of things that people have been computing in parts of string theory, where these formulas actually look very familiar. And this formula is indeed very geometric, and my talk will be about giving a geometric interpretation of this formula from the point of view of indeed of a dual description. But even sort of looking at the explicit math of this formula, even the physics of this formula is quite interesting, that the spectrum is really sort of has a maximum entropy state, because the spectrum doesn't sort of keep growing as it does usually for a CFT as a function of energy. It's also bounded over a finite range in energy space. One comment that actually might become important later is that once you've taken the double scaling limit, the operator algebra that sort of survives turns out to be of type 2-1, which is also suggestive of a potential dual interpretation in terms of de Sitter space. Let me also make one final comment. The fact that SYK has connections with the Schwarz and quantum mechanics, indeed, is sort of obviously a well-known thing. And for this talk, I'm going to be interested really in sort of this more global expression, and I'll be mostly interested actually in temperatures, beta, that are probing this range of the spectrum. But if you go to very low temperatures, which means that beta becomes large, then you're focusing basically on this little corner of the spectrum. And in this little corner of the spectrum, this spectral density will match with the Schwarzian spectral density. The sort of Schwarzian physics sits in that corner. Okay, so now I'm jumping to another sort of dual frame. So this came sort of from discussions indeed with David Giotto when we started talking about sort of the geometric interpretation of these formulas. He recognized that they indeed looked like things that were studied, like 15 years ago or so in supersymmetric gauge theories, and these things are called Schur indices. And they're basically supersymmetric indices, but then you can sort of make them into more interesting objects by having a fugacity that couples to a certain U1 charge. So you take a four-dimensional gauge theory. If it's superconformal, then it's the easiest definition. You basically put it on an S3. The J3 rotates the S3, so there's a fixed locus of the J3 action. And then there's also a circle along which you take a trace. But then, so this Schur index, again, can be explicitly computed. And the reason why that's possible is because, again, it's a supersymmetric quantity. It doesn't depend on the gauge couplings. So therefore, you can basically take the zero coupling limit and just compute these things. So I'm not going to describe in this talk how you're actually going to compute it. But basically, you count. Right? So that's how you compute this index. Here, I'm also giving the index a label beta. And this W1, it's a Wilson line operator, which is supersymmetric. And I'm imagining that I'm wrapping that Wilson line around that circle. And those are operators that are localized on the fixed locus of my U1 symmetry. So I get basically, famously then, also a one-dimensional system from the four-dimensional theory that lives on this fixed locus of the symmetry. But it turns out that because of this Q that sits here, that operators that are ordered along that line here don't commute. So there's a non-commutative algebra associated with this. And I'm going to be taking indeed the analog of a thermal partition function by giving that Wilson line some kind of fugacity. That's beta, that I call beta. For a later purpose, let me also mention that, of course, you can take other line operators here as well. You could take the tHooft loop, and you could wrap the tHooft loop around this, which would have, again, non-trivial commutation relations, in particular with that W. OK, so I said most of the things here. One subtlety is, again, that I'm going to be interested in the Schur index for SU2 gauge theory, pure SU2 gauge theory. That's not a superconformal theory. And it turns out that you have to work a little bit harder to actually give a good definition to this object. But I'm going to skip the technicalities of that. But this gives you the gist of what it is. Another technicality that I'll skip over is that one can generalize this notion of a Schur index, which is basically just a Witten index, twisted Witten index, if you want, to something that's called a half index, essentially by introducing a boundary and in some sense taking the square root out of the geometry or the square root out of the index itself. And it turns out that basically if you compute that particular half index for Seiberg-Witten theory, on the nose you're finding the same partition function as the partition function for SYK. So this is an experimental observation at this point. And then, of course, as a physicist, you would like to explain why that happens. And so what explains it? What can we learn from it? And if we can learn something from it, is this a special coincidence, or can we generalize this equality? Now, deliberately, I start a little bit with this slightly more mysterious duality, because a priori, from the physics point of view, SYK doesn't seem to have much to do at all with Seiberg-Witten theory. So this could just be one of these mathematical curiosities. And the question is, can we actually extract some physics from it? And it turns out that sort of the useful way of thinking about this is indeed sort of thinking about it from the string theory perspective, or more generally from the AGT duality perspective, where instead of the four-dimensional gauge theory, let's lift it initially to 6 dimensions, because now indeed I can start combining the four-dimensional gauge theory with some other manifold on which I'm compactifying the 6-dimensional 2,0 theory. And then for any choice of the 6-dimensional, of the 2-dimensional manifold, I get a particular 4-dimensional gauge theory. And for Seiberg-Witten theory, this 2-dimensional manifold is essentially, I keep forgetting which one is the double cover of which, but it's related to the Seiberg-Witten curve. We can call this thing the class S curve of the Seiberg-Witten theory. And interestingly, for Seiberg-Witten theory, this class S curve is a sphere, a two-dimensional sphere with two what's called irregular punctures. And it's because of the irregular punctures that this theory is actually not conformally invariant. I'm indicating here some wiggly lines that are things that live on that sphere. And indeed, in the AGT correspondence, what happens is that the Wilson lines that live in the four-dimensional theory are lifted to two-dimensional operators in the sixth-dimensional, two-dimensional line or the surface operators in the sixth-dimensional theory that are also then acting as line operators on this two-dimensional curve. Now, the curve by itself, of course, you want line operators that do something topologically interesting and non-trivial. In this case, it's a sphere with two punctures, and therefore there's a loop that goes around the equator. And that loop indeed will be the Wilson loop eventually. And there's not a loop that goes between the two punctures, which will turn out to be the tHooft loop. Now, what lives on this particular theory? In AGT, it was already noticed if you take the Nekrasov partition function on the, in 4 dimensions, that it lifts to the conformal blocks of a Liouville theory that lives on this curve. In the case of the Schur index, you can have a similar sort of mapping, where indeed the Schur index is also some object that naturally lives on that curve. Thank you. And that index, so time flies indeed. We'll see how far I get. And that index, it turns out to be equal to the partition function of SL2C Chern-Simons theory. So here I'm making a slight jump. So I talked about this as a two-dimensional space, but I can add a time coordinate to this. That time coordinate is basically a copy of the time coordinate that was used in 4 dimensions. And then when I add a time coordinate to it, then there's a 3-dimensional theory whose spatial slice might match with this particular 2-dimensional curve. And then the basic idea is that if you now compute the Schur indices of this 4-dimensional theory, they give you actually a partition function of this Chern-Simons theory that lives on this particular curve. Gaiotto and Teschner in the recent work with long papers where they developed something they call Schur quantization. And what the Schur quantization does, it actually makes use of these explicit expressions of the Schur indices to construct a Hilbert space, and they want to associate that Hilbert space with that Chern-Simons theory on that curve. Now, I have to start speeding up a tiny little bit. Again, these are formulas that in principle, again, have been sort of studied in more detail in the past, and actually also in more detail in a paper that appeared this past Monday by Collier et al., where indeed they sort of have been studying the thing that I call this complex Chern-Simons theory, sorry, the complex Liouville gravity theory. And indeed, it has a very natural connection with the 3-dimensional theory. And in the papers that appeared this week, pure de Sitter gravity kind of appears to have also a strong link with that particular theory, and it goes sort of through the same correspondence that we are familiar with that relates the Chern-Simons theory in 3 dimensions to Wesson-Witten theories in 2 dimensions. But in this case, we start with an SL2C Chern-Simons, which we can interpret as a first-order formulation of 2+1 gravity through this particular redefinition of the sort of the spin connection and the dry bind, and indeed with this identification of the coupling of the Newton constant. And then if you go through the usual sort of construction where you try to associate a boundary degrees of freedom to this 3D Chern-Simons theory, you get a 2-dimensional Liouville theory that actually has complex central charge. And the interesting thing is that since this total central charge adds up to 26, you can turn this into the world volume theory of a string theory, or at least a 2-dimensional gravity theory, where you basically take the partition functions of the two theory and you integrate over the space of all metrics in 2 dimensions. And the interpretation of that is that what you're doing is you're basically constructing initially the states of this theory by considering the partition function of this thing. And then when you start integrating over the metrics, you're taking the inner product between those states. That's indeed the proposal also that was in this recent paper by Collier et al., that you take, you can start computing even amplitudes if you wish. And then if you put this two-dimensional theory on some space of some topology, we're interpreting that as an expectation value in the three-dimensional theory. And for us, that expectation value lives on this particular sphere with two punctures. Now, if we're going to interpret this thing as three-dimensional de Sitter gravity, then this sphere is really what the spatial section of the Sitter space looks like. Because then the only thing that we've done now is we've actually added two singularities, and that's the observer, basically, that we would imagine that would live, say, at a particular point. And then there's another observer, or at least maybe an image of that observer that lives at the other point. And now we can sort of start studying, basically, the partition function of this theory. And I claim that I can do it very quickly in the next 3 minutes. Or how many minutes do I have? 0 minutes. Okay. That went very quickly. Okay, also I'll go very quickly through this thing. So basically what we're looking at the phase space of this particular. Is that really true? What time is it now? Okay. We're looking at the phase space of this theory. We're basically sort of parameterizing that space, and we look at what it looked like classically. So on this slide, I'm just showing you the classical parameterization of that space. And it turns out that basically there's a classical geometry associated with the two Wilson lines, namely this line here and that. And there are some equations that you can write down, which are true for the classical object. But part of the whole point is that, of course, we want to do quantum theory, and then this Q starts showing up because we have a Chern-Simons theory with non-trivial braiding. And then it turns out that these relations precisely actually match with this Q-deformed harmonic oscillator through a set of identifications that you can easily find. So this is how basically the quantum problem in the 2+1 dimensions matches already with structures of the SYK model. In the last sort of minus or 30 seconds, I'll give another derivation of this same sort of partition function, essentially by computing a three-dimensional partition function with this particular line that connects the north and the south pole, and by taking the inner product between two of these things, I get a three-dimensional manifold, which is, say, a Euclidean S3 with a circle in it. That circle is indeed sort of a singularity, and I'm imagining that there's an observer living there. But I can think about that same geometry as obtained in this particular way, where I glue together two tori. If you do that in the most general way, these two tori, basically, they're S modular S dual to each other, so there's an S transformation between the two. And more generally, what one can do is one can actually take this inner product between these two torus partition functions and compute that. And you can do that in terms of the modular S matrix and also including the T transformation in general as well. And you can get partition functions of this particular type in the 2+1 dimensional gravity theory using the modular S matrix of this Liouville theory. And it turns out that this expression indeed exactly matches, again, with the SYK partition function. So that was sort of the goal of my talk, is to give you sort of a geometric interpretation of what the SYK partition function is. And it's summarized basically, indeed, by this three-dimensional partition function with one singularity. And it turns out that, you can start looking at other comparisons between the partition function that you obtained in that case and potentially even the usual thermodynamics that one would expect from 3D gravity. From the Lorentzian perspective, the interpretation would be is that this particular line that I've been considering describes that particular observer. And indeed, one can sort of find a nice correspondence between the dependence on this angle theta that I had in my story and the dependence that you would expect from having back reaction in 2+1 dimensions, where the observer, if the observer carries a certain amount of energy, would create a certain conical deficit. So this is sort of the conclusion is that there's a very quantitative way of connecting the double-scaled SYK model with computations that you can do in a three-dimensional theory that, for all practical purposes, again, looks like a quantization of a positively curved space. There are many things that I've not been discussing. Indeed, there's a whole list. And indeed, since I'm over time, I will not go through the list. But if you want, you can pick one or two of these things and ask them as a question. Thank you.
Okay, one quick question. Yep, Alejandro.
From the 4D point of view, the theory was supersymmetric. So what's the role of supersymmetry in the 1 or 2D situation?
Right. So this goes back even again to the AGT correspondence as well. In that case, the Nekrasov partition sum was also could be computed in 4 dimensions as a supersymmetric object. It's a sum over supersymmetric solutions. But the supersymmetry of the 4-dimensional theory is not lifted to a supersymmetric action of supersymmetry in the 2 dimensions. The only thing that you know in the case of AGT is that the 2-dimensional dependence on the moduli of the 2-dimensional surface is holomorphic. That's the holomorphy of the gauge theory. In this case, everything is topological. So the fact that we were able to define an index, that's where the supersymmetry was used in 4 dimensions. But the index itself is just a thing that depends on Q, and then no longer supersymmetry in the 2-dimension, in the dual description.
Okay, thank you. I think in view of time, let's go to the next talk, and let's thank Herman again. Lenny? Well, maybe we have time for one more question. So, Fernando, you wanted to ask a question?
Yes, it was very tempting to ask you about your next to last point. What can you say about inflation and dark energy?
So what was
your point? The next to last point.
Inflation.
Inflation and dark energy. What do you have to say about that?
Let me just be very quick and maybe diplomatic about this. Is that again, Lenny, who will talk now in a second, and I have been looking at this system at very different energy scales. I have explained a structure that lives at a certain scale, as Lenny will probably explain, and Lenny will sort of be looking at a much lower energy scale. And my interpretation is that what I've been looking at is sort of at something where the curvature is sort of at the inflation scale, and what might emerge at later times.
Okay, well, thank you. And our next speaker is Leonard Susskind. So, Lenny.
First of all, thank you, Ahmed. Thank you not only for a fine, fine conference, but also for the little adventure we had yesterday. You don't have to know. I also want to thank somebody else. I want to thank Sandoz, who's been incredibly helpful. I don't know if she's here, but I think we should collectively thank her for an enormous amount of help. Okay, I'm not going to do at all what Herman said I would do. My sense of what Herman is doing is that he's inventing some very powerful tools, and those tools may well help us nail down this question of whether SYK at infinite temperature in the double-scaled limit is or isn't de Sitter space. And much of what he says I agree with, but there is a point of strong disagreement about some of the physical interpretation. I'm not going to talk about it. I will simply say you can read about it in recent papers that I wrote with Adele Rahman. Okay. Now, if you appreciate beautiful things and you appreciate art. Oh, nobody heard what I said until now? Okay. I think I have to turn it on. Oh. Oh, I see. Oh, thank you, Juan. I can use that.
I don't know how to put this.
Ah,
Yeah, why
don't worry
use
about
this?
it. Okay, let's just disconnect that.
Okay. I'll take it from.
Hello, can you hear me? Yeah, okay. Okay, if you appreciate beautiful things and you're a lover of art, I invite you to look at some paintings by a painter who I knew very well, recently died. But there's one of her paintings. Anyway, how do I operate this thing? Ah, there it goes. All right, so I'm going to talk about a very interesting parallel between QCD and DSSYK infinity, double-scaled SYK theory at infinite temperature. And you can see that there's a couple of authors there. Let's see. What's wrong with it? Ah, no, that went back. Now forward, come on, there we are. Okay, so let's think about QCD for a moment. I'll start with the QCD side of things. There is an tHooft coupling. I'm thinking about large N theory. There's an tHooft coupling, which I'm going to call alpha because I don't want to call it lambda because lambda stands for something else. So there's alpha, and the tHooft limit is N Yang-Mills goes to infinity with alpha fixed. For example, in ADS5 cross S5 cross CFT, the tHooft limit turns out to be a limit in which the string length scale divided by the ADS length scale, the radius of curvature of ADS, is 1 over g squared in, which is 1 over alpha to the 1/4 power. In other words, fixed alpha, fixed alpha is fixed string scale to the ADS scale. Now, that's a limit, if you think about it, in which the universe, the ADS universe, is getting bigger and bigger, but the string scale is getting bigger and bigger with it. A more interesting limit in many ways would be a limit in which the string scale stays fixed as the ADS radius gets big, and that's just not the tHooft ratio, the tHooft limit. In tHooft limit, the ratio of string to ADS scale is fixed. Okay, now there's another interesting limit of field theories, gauge theories in particular, the fixed G limit. That's the limit not in which the tHooft coupling constant, but in which the Maxwell coupling constant or the Yang-Mills coupling constant stays fixed as n goes to infinity. And in that limit, that's, you call that the flat space limit, that's the limit in which the ratio of the string scale to the ADS scale goes to 0 as the ADS scale gets bigger and bigger. And that limit exhibits, or should exhibit, sub-ADS locality, which is a very confusing but extremely important part of holography, to understand local physics in a limit that the universe gets very big. Okay, so that's one example of the importance of this fixed G limit. If I don't tell you anything else, and I don't get very far in this seminar, let me tell you that I think the fixed G limit is extremely important and very poorly understood. Okay, the same kind of limit occurs in BFSS matrix theory with the tHooft limit. The analog of the tHooft coupling constant is something which involves some energy scales and so forth. But let me make it short. The tHooft limit is the limit of 10-dimensional D0 brane black holes, whereas the fixed G limit is the 11-dimensional theory, 11-dimensional M theory. And clearly the fixed G limit is far more interesting than the tHooft limit if we're interested in this duality between matrix theory and 11-dimensional flat space M theory. Okay, another example of the fixed G limit. Oh, let's see what happened here. Hold on, come on. I'm not sure what's going on. Am I doing something wrong? There we go.
Can you
No. Yeah. Okay. Another example is the double-scaled limit of SYK. That's also an n equals infinity limit, but in that limit, lambda, which is p squared over n, is held fixed. And what I'm going to tell you today is that limit is very, very similar to the fixed G limit of Yang-Mills theory. Okay, so let's... Why isn't this working? What's that? Hmm? Point it that way? Okay. Oh, I see. I see. Okay, thank you. Thank you, Daniel. Thank you very much, Daniel. Okay. So we're going to be talking about QCD, but in practice, I think we're going to be talking about QCD in a box, a spatial box. That's not going to play any big role. It does, but not for this seminar. Okay, every diagram, Feynman diagram, every diagram can be written as a ribbon diagram. You know the story about ribbon, the tHooft diagrams, and so forth. And every Feynman diagram has a genus associated with it, which is the genus, the lowest genus surface that the diagram can be drawn on without cross lines. For example, this, whoops. Yeah, the first set of, the diagrams that I've drawn there, they're diagrams in this case for a, perhaps a gluon correlation function. Those are genus 0. They can be drawn on the flat plane without cross lines. The flat plane is the same as the sphere, so those are genus 0 diagrams. Next, genus 1 diagram. Next, genus 1 diagrams. Genus 1 diagrams, the simplest one, is the pretzel diagram. The pretzel diagram with 2 punctures. A pretzel with 2 punctures, how about that? And if you ask what the value of that diagram is, it has 4 vertices, that's g to the 4th, period, but that's also equal to, what does it say, alpha squared over n Yang-Mills squared? Alpha squared or alpha? Oh, well, it doesn't matter. Alpha squared, okay, alpha squared over n Yang-Mills squared. Go to the next one. The next diagram is the cross diagram there, which is also genus 1. That's g to the 6th n Yang-Mills, and that is equal to alpha squared. Also says alpha squared, alpha cubed. I can't see it from here. Alpha cubed over n Yang-Mills squared. Notice they have the same value of the denominator, n Yang-Mills squared, and it's the denominator which tells you what the genus of the diagram is. Okay, so all those diagrams scale like 1 over n Yang-Mills squared, and they are genus 1. I can write those diagrams, or I can write the result in a different way. The first diagram is just just g to the 4th. The next diagram, g to the 6th times n Yang-Mills, that happens to be g to the 4th times alpha. The next one, you keep going up, they're all g to the 4th times powers of alpha. All right, so the sum of those diagrams is g to the 4th times some function of alpha. At each genus, the answer is some function of alpha. Well, there are 2 ways of writing the answer. One is the standard tHooft way of writing it, a sub h over alpha times n Yang-Mills to the genus, but the other way of writing it is that they are g to the 4 times the genus times a function of alpha, where the function of alpha is also a sum of terms. Okay. All right, what about the fixed g limit? In the fixed g limit, alpha goes to infinity. So all we have to do to get the fixed g limit is take those functions of alpha, which appeared in the second form of the relationship, and simply evaluate them at alpha goes to infinity. The amplitude is sum over h, sum over genus, g to the 4th to the genus, times a number f, or not times a thing f, which is the limit of this function of alpha as alpha goes to infinity. That's the fixed g limit, if it exists. Of course, it may not exist. We have to take a limit. That limit may diverge. It may do something stupid. It may go to 0. I don't know. It may have singularities as you try to get to large alpha. But if the limit exists, this is the way you get it. Okay, now, another way of thinking about it is g to the 4th Yang-Mills is expected to be g squared string. This is simply the relationship between open string coupling constants and closed string coupling constants. G to the 4th Yang-Mills is g squared string, and so what this amplitude actually looks like is a sum over genus of a string coupling constant to the twice the genus times a thing which we can sort of identify with the world sheet partition function for that particular genus. In other words, this form, g string to the 2h times a function of h, and where n has disappeared, incidentally, that's the main point, n has disappeared. This is the connection, if you like. It's a tHooft connection between string theory and in large n limit and Yang-Mills theory, if you like. Okay, I think we just did that, didn't we? Yeah. Okay, now let's turn to double-scaled SYK theory in the limit of infinite temperature. You all know, or you don't know, the SYK Hamiltonian. You probably recognize it. The j squared in the brackets there, that's the variance of the random set of coupling constants. And it is equal to script j squared, fancy j squared, which is just a number, times p factorial over n to the p minus 1. I'm working in units which I call cosmic units. They differ a little bit from the standard units by a factor of p. Ignore that if you don't understand it. Just accept that I know how to do dimensional analysis. And that's the Hamiltonian, the j's in cosmic units. Lambda is by definition p squared over n. Strictly speaking, it's twice p squared over n, but ignore that. And the limit is the limit of fixed lambda as lambda goes to infinity. Sorry, as n goes to infinity. What I'm going to tell you is that this limit is very, very similar to the fixed g limit of gauge theory. The other thing is, of course, that the Boltzmann temperature is infinite. Okay. How do we calculate in this theory? Many, many possible ways. But one dumb way is just to do perturbation theory. Perturbation theory in J. Now that seems a little strange because the whole Hamiltonian is J. But if you look at the action, it contains a quadratic term and terms with products of p fermions. You can do perturbation theory. We'll see what happens if we try to do it. The vertices of the theory contain interactions or contain vertices with p fermions coming out of them. That's these terms, psi up to the power p. The propagators for the fermions are just epsilon of T1 minus T2, the sine function. The red line coming out just represents the j coefficients themselves, which we're going to integrate over. Why do we integrate over them? We integrate over them to do ensemble average. But because we integrate over them, we can effectively think of them as fields. And they have propagators. The propagator is very simple. It doesn't even depend in time at all. P factorial over n to the p minus 1. And we can start trying to calculate correlation functions. There are graphs. The first graph is just the basic propagator of calculating a two-point function, just the basic propagator of the fermions. The next graph is a Mellin graph. Mellin graph, well, you see it. I don't have to explain it. How do we calculate it? Well, it's pretty simple. They're a lot of fun to calculate these diagrams. The two vertices in the Mellin graph give us j squared. The red propagator gives us p factorial over n to the p minus 1. We have to figure out how many different ways are there of picking the indices, the fermion indices, on the p minus 1 internal lines in the Mellin. That's n to the p minus 1 combinatoric coefficients in the the limit of large N and large P. It's just n to the P minus 1 over P minus 1 factorial. And then there are some time integrals to do over the vertices. The time integrals over the vertices, there are two time integrals to do. Oh, tau, yes, tau is just the time at the endpoints, psi of 0 times psi of t. And it simply gives us what I've written there, the time integral is just tau squared. I'm going to write that in the form the n to the p minus 1's cancel. P minus 1 factorial in the denominator cancels a lot of stuff in the p factorial. We get j squared to the p, j squared times p times tau squared, and I'm going to write tau squared as tau minus times tau plus. Tau minus represents the time, the relative time between the two endpoints on the melon, and tau plus is the integration of the center of mass of the melon over the interval between 0 and tau. Okay, so there we go. That's a calculation of it. I'm being a little bit loose. Okay. The way. Yeah. Here's another graph up above. Oh, we'll go back to the original graph. It contained no n's in the denominator. I'm going to call that genus 0. This has nothing to do with topology of surfaces, but just because it contains n to the 0 in the denominator, I'm going to call it genus 0. The next graph, I'm not going to go through it. It just gives you j to the 4th times p to the 4th over n times tau minus cubed. There are now now 4 time integrals to do. And that having an n in the denominator, I'll call genus 1. There's some more diagrams. I'm not going to go through them in detail. The bottom diagram is a genus n minus 1 diagram. And so it goes. Lots of fun. Calculate these diagrams. Okay, what's the basic message? Each diagram is of the form some power of p divided by n to the h. N to the, by definition, h is the genus, which is just actually the power of n in the denominator. So there's not much here except to say that it's a function of p divided by n to the h, where the function of p is a power series in p coming from all the diagrams of that genus. Well, recall that in the Yang-Mills theory, the amplitude is equal to the sum over the genus times a function of alpha divided by n Yang-Mills to the power of the genus. They look a lot alike. In fact, they look isomorphic. They look the same with the following identifications. N Yang-Mills squared is like n of the SYK system. Why is that? Well, n is the number of degrees of freedom in the SYK system. N Yang-Mills squared is the number of degrees of freedom in the Yang-Mills system. So it makes sense to make that identification. In any case, the formulas make that identification. If you look at the formula, you'll see that alpha corresponds to p. Alpha, the tHooft coupling constant, corresponds to p, the p of the SYK system. And finally, g to the 4th Yang-Mills is like lambda. Now, how do we see that? Well, first of all, g Yang-Mills squared times n Yang-Mills is by definition the tHooft coupling constant. Divide it by n, square it, and you get g to the 4th is alpha squared over n Yang-Mills squared. Alpha to squared is like p squared, n Yang-Mills squared is like n, and so g to the 4th is like p squared over n, according to this correspondence. So g to the 4th Yang-Mills is like lambda. P squared over n is lambda. The fixed lambda limit is a lot like the fixed G Yang-Mills limit. Why this is true, why this correspondence exists, I don't really know. Yeah. So what should I do? Okay. Sorry about that. I'm not good at this. Okay, so that's the correspondence. Let me graphically show it to you pictorially. The Yang-Mills theory, we can plot n Yang-Mills against alpha. The ordinary tHooft limit is fixed alpha, and it just means moving upward vertically along the blue lines. You can go to larger tHooft coupling constant, which means we'll move out far, but going up along the straight lines vertically is the tHooft limit. Going out along radial lines is fixed ratio of n Yang-Mills to alpha, and that's the fixed g-squared limit. So that's the meaning, that's the graphical meaning of these two limits, and they are different. In the SYK system, we can plot p against square root of n. Those are the corresponding quantities. And the standard SYK system, a fixed p is like moving vertically upward, and the double scale limit, which is fixed lambda, is moving along these radial lines. So there's some correspondence. Now, you just stop me. I actually said most of what I have to say. Okay, but there's a lot more. Okay, now, let's see if we can improve our approximation. Instead of using, this actually covers everything, or all possible graphs, replace the bare propagators inside the melons by, let's call them dressed propagators. Dressed propagators contain melons within melons within melons. Each line is decorated with all the possible melons, together with the melons within melons, and so forth. These diagrams can be summed, the ensemble average of them, they can be summed by Schwinger-Dyson equations. And what we find is that the epsilon of t, which is the bare propagator, is replaced by epsilon of t times e to the minus 2jt. It's a very simple thing that the sum over the melons gives us. Yeah, okay. Okay, good. All right, so we can improve the whole story a lot by making this replacement. Now, in the internal structure of the melon, there are something like p single particle propagators, and that means this epsilon of the epsilon times e to the minus jt gets raised to the, in this case, the p minus 1 power, but don't worry about the difference between p and p minus 1. And what we find out is that we should simply replace every propagator, which was just an epsilon, by an epsilon times e to the minus 2jp. But now, the integration over the relative coordinate between the incoming line and the outgoing line, that integration now, it's the integration over t, is highly convergent. It converges quickly because of the exponential fall off. We can do that integral very simply, of course, and it just gives us 1 over pj, or 1 over p minus 1j. And the prescription now is in each of those diagrams, replace tau minus wherever you see it, namely the time between vertices or external vertices on the melon, replace it simply by pj. That is, okay, let me just show you one diagram, what happens when you do that. If we went back to this diagram up on the top there, which was genus n minus 1, for example, j to the 4th with all those p's, every tau minus gets replaced by 1 over jp. If you do that, you will find out that what this diagram gives you is p squared over n to the genus n minus 1, p squared over n to the genus, that's lambda, lambda to the genus, times a factor jt, which occurs for every diagram, so I just write it in blue and throw it away because it's not interesting. This is general. This is very general. When you dress the internal propagators, oh, what's interesting here is n has disappeared. N has disappeared, and this is telling us that there's a good large n limit in which n drops out, which only depends on lambda, like the hoped for fixed G limit in Yang-Mills theory. Okay, there's a whole bunch of other diagrams. They all do the same thing. They're replaced by lambda to the genus, and it's as simple as that. Okay, I'm just about finished now. I'm not finished. I could go on and on for hours, I assure you, but we won't. Okay, what's the Yang-Mills analog of the form? Well, let me go back a step. Yeah, the general formula, as I said, is lambda to the h. That's like g to the 1/4 to the h. So if lambda is replaced by g to the 1/4, then lambda to the h becomes g Yang-Mills to the 4h, and g Yang-Mills squared is like g string in the correspondence between strings and Yang-Mills theory. So that means that each diagram is lambda to the h is like g string to the 2h. What does that mean? That's exactly the g dependence that we expect for a genus H worldsheet diagram. Each handle gives you a factor of twice g string, 2g strings, g string squared, and that's why we have g string to the twice the genus. Okay, I'm pretty much going to finish up now. What's going on here, I don't really know. These are empirical observations about calculations. Some kind of unusual correspondence between Yang-Mills theory in the fixed G limit, also in the fixed tHooft limit, and corresponding limits in SYK. Why it's true, I wish I knew, I don't. Does it suggest that ds SYK infinity is a string theory of some kind? I don't know. If it isn't, then what is it? I don't know. But maybe the French had understood something when they said that the word chord is the word for string, and I think maybe they did have something. I'm going to leave it at that. And if you like, you can come next week.
Questions? Over there.
Thank you. So how about the temperature? Temperature, like the two temperatures of the sitter. You have the infinite temperature and also a finite one according to
The temperature.
temperature.
Temperature. Yeah. The temperature is evaluated. The formal Boltzmann temperature is evaluated at infinity. Does that correspond to the Hawking temperature in the de Sitter space? No, it doesn't. For that, I'll refer to a paper by Herman Verlinde and myself about a quantity called temperature, which is a little different than temperature, which really is the Hawking temperature, if there really is a correspondence with de Sitter space. I won't try to explain it here.
But how about in your picture with the Yang-Mills, for instance?
Who's
That
asking
was,
me? Where?
yeah, here.
Oh, I see. The sound is coming from there.
Oh,
Yeah.
in
I'm
your,
a very old-fashioned person. I was born before the microphone was invented.
okay.
You believe it? You don't believe it?
Yeah, in the
I was
Yang-Mills.
born before the wheel was invented.
Okay. Yeah, in the Yang-Mills picture that you have for the correspondence, how do you see that there should be like two type of
How
temperature?
do you see what?
That there should be like two type of temperatures, an
There
infinite one
should
and
be.
two type of temperatures, like a temperature and an infinite one, the Boltzmann.
Temperature? In the Yang-Mills theory, actually, we could be doing Yang-Mills theory in a box at 0 temperature. It's just a structure of graphs. That's all we're talking about. It could be any temperature. The graph structure is always the same of perturbation theory. So it's a correspondence. It's not a correspondence in the fact that the numerical values of the diagrams are the same. It's a structural correspondence, and that structural correspondence is largely independent of the temperature. Okay.
Okay.
Any other question? Over there.
It's largely independent of the Yang-Mills temperature, not the SYK's temperature.
What is the analog of gluons in double scale SYK?
Sorry, what is the analog of what?
Gluons in QCD.
Gluons.
Yeah.
The single fermions behave to a certain extent as similar to gluons, but it could be two fermion pairs. It's just a small number of fermions. So in the Yang-Mills theory, I drew diagrams coming in with gluons, for example. In the SYK system, the things coming in and going out were single fermions. But the structure of diagrams doesn't depend terribly much on what the external lines are. Whatever the external lines are, the topological structure of the diagrams is very similar. Again, I will emphasize that these are empirical observations gained from lots of calculation of these diagrams, and I don't really know why that correspondence exists. It's a mystery.
Okay, thank you. Let's thank Lenny again.
Thank you.
Just a quick announcement. You're done. Thank you so much, Lenny. So there are new posters outside. Please have a look at them. They're going to be posted for until the end of the conference. We're going to be back, so we're going on a coffee break right now. This coffee break was supposed to be an hour long, but we're cutting it short. We'll be back in half an hour. Okay? So what time is it right now? So we'll be back at 4.